So hello again. I will talk a little bit about Wendelin R&D project, considering that I have only a few minutes. My name is Tyagov. I'm responsible and project lead of both Wendelin R&D projects and the entire generic platform called Wendelin, which you just heard about. The project itself is EU funded. It has started roughly 3.5 years ago. Its total cost is 2.5 million euro. The participants in these projects are us, Nexedi as a project leader, MariaDB, and Micromega Dynamics, which are part of Wolfram Group. The goal of this project is to extend the generic Wendelin platform and make it available for wind turbine management, and additionally to produce a so-called smart sensor which can utilize GPU for anomaly detection in the work of a wind turbine, something which you already heard about from Dr. Wolfel, and detection mostly of anomalies in the turbines, which include ice, problems with the bearings, structural damage, and stuff like this. So here it is the main outcome of this project, which is the so-called DAC-SCOM/18. It is a smart sensor. You see it now in its industrial case with passive cooling on top of it. On the right side, you see the main component of this sensor. It is an NVIDIA TX2 board, which has bundled inside a GPU, which we use intensively for anomaly detection. I will talk a little bit about the smart sensor, what is interesting for them, and our idea was that these sensors should be placed inside or nearby a machine. In our case, for our project, this is a wind turbine. We usually place them in the so-called nacelle. This sensor is able to provide a real-time computation of an anomaly index, and respectively, if the sensor sees something, it will certainly do some actions to prevent failure in the wind turbine, or just shut it down, or raise an alarm and warn some human who can do further actions. A few words about the sensor itself. It is 10 by 7 centimeters by 10 centimeters, quite small. It is actually two computers. First one is a so-called acquisition unit. It is running in real time based on a Texas Instruments chip. It provides a low-level interface to the so-called SNC sensors, which collect vibration data. And the second one is what you see actually, and what I said, the TX2 board on the right side of the diagram. It has non-real-time Linux operating system. It's Ubuntu 16.04. It has NVIDIA libraries. It has our own embedded software called Windelin. And it provides high-level computation using machine learning models. What's important about these sensors, and was a main requirement during the development of it, that it needs to work without any internet connectivity. You just imagine a wind turbine somewhere offshore or in the middle of nothing. You don't have internet, or if you have, it's quite unreliable. How does it work? Well, it uses machine learning for failure prediction and anomaly detection. I will explain a little bit more how we did it. And I have a question. Who does machine learning here? Cool. What's interesting, what we find out during the work on the project is that we are able to build a model on the server side, and we are also able to have the same model integrated into the embedded environment, which for us means that it's less coded to maintain. It's just one model, and it works, usually. So machine learning simplified. I have to try to fit into a few minutes this big topic. So we have three important things. It's the data. In our case, and in most cases, this is usually a set of numbers representing a machine state. In our case, it's a wind turbine state. We have a model which is basically a mathematical formula for converting with minimal losses input data to output data. We have a model which is created by iterating over and over terabytes of data multiple times. Actually, the model itself is a very small file which is quickly executable on recent GPU architectures or CPU architectures, because in our case we use TensorFlow and Keras, which run transparently based on the hardware capabilities of the board. And we have actually the most important stuff is the so-called anomaly index. In our case, it's basically, simply said, how well the inputs are coming from the sensor data fits into our model. The less it fits, the more anomaly index goes up, and we can detect an anomaly based on certain thresholds. In the picture, you actually see autoencoders, which we use heavily to detect anomaly index. You see here some data, which in our case is an image, which itself can be represented by a matrix of floating numbers. And how autoencoders work? Okay, you have an encoder function, you have a latent representation in the middle. We have a decoder function. And at the end, you have a reconstructed output out of this formula. So what is, in our case, the machine learning? It is making sure that left side is as much as possible on the right side. To do this, we find out that we need a lot of data. In the case of wind turbines, at least 8 to 10 months of data. We also find out that each wind turbine is different from the other wind turbine. This is a little bit about the context. Do we have enough time? 4 minutes? Okay. So some more words about the smart sensor during the projects and the lessons we learned. First, we find out that this work is actually quite generic. It's any industry applicable, as long as you can get your data in. If you have some kind of abstraction, or in our case, the so-called acquisition unit, most of the code we do is actually quite generic. And the sensor itself can be quite generic, of course, based on where you want to put it in. In our case, the communication between the acquisition unit and the data processing unit comes over TCP/IP protocol, but it can be anything else as long as you can get your data in. Machine learning is, I hope, no more a black box, and it's based on real mathematics and theories. We also find out that it could be very useful that we work on the server side and develop models there. Anyway, we have to do this this way using powerful GPU cards, and use the same model at the client side, which is in our case is the SNC model. The big lesson learned is that this approach of working in a generic and abstract way is really useful and can be applied to almost any industry as long as you can train your models well and as long as you have enough data. Since we have not so much time, I thank you, and I'm here for your questions.
Question. If you're using a neural network to define your model.
Can you repeat the question?
Okay. So if you're using a neural network to define your model, it's almost impossible to guarantee the output for any of the possible input scenarios that you have.
Yes.
So is this a problem when it comes to certification or proving that your device will always work in a critical system?
So the question is if we can guarantee that input data is exactly the same as output data, more or less.
Yeah.
And if this is a problem for certification, so first the project is in its pre-industrial state, which means that the next step is certification. But there is a long way to go to there. First is being able to certify the Linux operating system first.
I can reply legally.
Okay.
Yeah. So give
Oh,
me.
I give
I'll give you the
answer,
legal
the legal reason, then I explain the technical.
Yeah. So I need this. Okay. So is machine learning deterministic? That's the question. And what's the relation with security certification? So if you go to countries like France and all countries with similar industrial security laws, it's unacceptable to use machine learning because you cannot prove in a deterministic way that it will handle any scenario of risk. So in France, they define a standard scenario of risk, and then you have to prove in a completely deterministic way that the factory will not go beyond that scenario. If you are in the Netherlands, there is the idea of probability that is accepted in the law. So the approach to industrial risk in the Netherlands can use not only reference scenario, but also a distribution of scenario. So with such ways of considering law, why not statistics also for security? So it really depends on the legal culture. Wendelin project was initially started for nuclear industry in France and was suddenly stopped when they found they would never get any certification. Then we moved to another application. Last talk, because we have to hurry.
Okay.
No, now it's